Our last talk for today, and this is the talk of Professor Ratu from Lausanne. Please.
Thank you very much. First, I want to thank the organizer for the invitation. I'm by no means somebody who does liquid crystals by profession. I came in to the field in a completely convoluted way and sort of stumbled onto it. I'm doing geometric mechanics. I'm interested in the geometric aspect of fluids and so on. Of course, complex fluids showed up. And one of our great influences, both of my co-authors, François Guébalma from the École Normale, CNRS, and Cesare Tronci from Surrey, was the influence of Daryl Hone. I mean, there is no question. I mean, it was one of his papers that sort of started us thinking about it. I want to start with the punchline. I'm going to give you my talk in 3 minutes, right? And then I'm going to explain all the words, okay? So, there is a problem in some of the community, and I was actually surprised that I didn't see it here. There is a controversy that's been going on for almost 15 years. It is the model of Ericsson and Leslie and the model of Erringen. And Erringen claimed correctly that his model includes Ericsson-Leslie. He wrote 2 papers, both of them have mistakes, mathematical mistakes. He just made them computational mistake. And this has created a lot of controversy. I'm going to show you at least one paper like this. We solved the problem. It is true, Erringen was right. But the methods by which we solve it are quite unusual. We are using some heavy machinery from geometric mechanics. There's a lot of geometry involved. And I would like to show you this. And there is much more going on, in fact. So this is my talk. This is the problem. The problem is solved. We did it. It's over, right? We can all go home, right? Okay, now let me show you what I'm doing. Okay. So, I want to show you the 2 models. One of the models, I'm going to go very, very fast over it because you're much more experts in it than I am. Then I will show you sort of the workhorse of the theory in the easiest possible way, the way Poincaré stated it in 1901. Then I'm going to show you what we need. We need a significant extension of the same theorem. And then I'm going to show you how this theorem applies to the 2 models. And then I'm going to show you that Erringen implies Ericsson-Leslie. Erringen was a professor of chemical engineering at Princeton. He died 3 years ago. We, in fact, François and myself wanted to send him our first paper in which we actually dealt with liquid crystals, but it was too late. At the venerable age of between 78 and 80, he has written 2 volumes, and I highly recommend them. It's quite something. I said that he made mistakes, but I mean, let me point out that I found only 2 of them, and the second one I'm not even sure it's a mistake. Maybe I don't understand what's going on. And after I show you the geometry and the algebra involved in doing this, I am in awe how did this guy compute? I don't know. I mean, he did it by the seat of his pants in an incredible way. I mean, you will see what's involved in a second. So, in order to understand, what did we do? We cut out all the dissipative terms. I know we shouldn't do this, but okay. We start first with the conservative term, understand the geometry, then we add the dissipative terms. Like you understand first Euler, and then you understand Navier-Stokes, and then you put them together by a Trotter product formula, for example, right? All the boundary terms are gone. So I have no K2 plus K4 terms, no K13, they're all finished. They're gone, right? Because they integrate to 0. And it's all formal at this point, and the whole field screams it needs analysis. Okay, so the 2 theories that I want to talk about are the director theory, which is due to Hossein, Frank, Zöcher, Ericsson, and Leslie, which you have heard much more than I can possibly tell you about it, and the so-called micropolar, microstretch, or micromorphic theories of Erringen. I'll tell you more about this in a second. And then there is a third one, which is the ordered micropolar approach due to Lhuillier and Rey. Again, I haven't heard anybody talk about this here, which combines the director theory with the micropolar theory. We know how to handle this. I will not talk about it. So all we are going to discuss is nematic liquid crystals. So K1 is 0, the first one for chirality. And as I said, I set all dissipation equal to 0. I'm working in a bounded domain in R3. No boundary, flat torus, whatever you want, right? Smooth boundary, all boundary terms are 0 or there is no boundary. I don't care. Whatever it takes to kill the boundary terms, I do it very cavalierly. And I fix a volume 4 mu on D. Okay, so here is Erickson-Leslie. So the way I, as a mathematician, understand this, I have some very primitive view of this. You know, you have a fluid, they're just particles, and each particle carries a little arrow, and it moves again around with the arrow. That's for me Erickson-Leslie. And this is given by n, and of course n has to be identified with minus n. And here are the Erickson-Leslie equations. So I put them here so that you see my notation. U is the Eulerian velocity. F is the internal energy density. I put here rho minus 1, that means 1 over rho, because for whatever reasons, it's easier to write the energy in terms of 1 over rho than over R. We picked it up from books. Here is the second equation that involves n, the director field. J is the micro inertia constant. F depends on n, and on the gradient of n is the free energy. ddt is standard notation for us in geometry. This is material derivative, it's a covariant derivative. And H is the molecular field, and it has this expression. Okay. So of all the pieces in the energy that I care about, this is all I see. The other ones are divergences, so I don't care. So here are the usual pictures of what they mean, splay, bend, and twist. And the question is, first question, what is the variational Hamiltonian structure of this equation? They're conservative, right? So on religious grounds, this better be Hamiltonian, right? So, okay, I will answer this. What does Erringen do? Erringen does something completely different. It's actually quite beautiful what he says. He says there are no particles. The fluid is formed by little blobs of quasi-rigid bodies. Imagine jello, like we eat in the morning or whatever, right? And you know, it moves and it stretches and it does all sorts of things. Each particle is that. So there are no more particles, there are only these little blobs around. And the examples that he gives is going beyond liquid crystals. Liquid crystal, blood, polymer melts, bubbly fluids, suspensions, all sorts of things. And he developed this in a long series of papers. Here are the earliest ones, but it goes on. It goes on all the way to 2000. Okay, so what does he say? He says, here I have a material particle, and it's characterized by its position capital X and by a vector psi attached to P. And that denotes the orientation or the intrinsic deformation of P. Both X and Xi have their own motions, right? So X is a fluid, so it moves, right? Here is the Eulerian or spatial position of the fluid. It's eta of X and T. And the Xi also is going to move to a Xi that depends on everything now, right? And he calls this the macro motion, and he calls this the micro motion. And both have equations. Now, the second key assumption is that these bubbles are very, very, very small, right? Okay, they are not particles, but they're damn small, right? So therefore, because they are so small, I'm allowed to think of this as linear in capital Xi, right? So he makes this assumption. And this capital Xi now, and this chi of X and T, this coefficient, this matrix that sits in front of it, it better be a 3 by 3 matrix that preserves orientation. That's what he says. Now, the classical Erringen theory consists of only 3 types of, that's what he does. So it depends what groups you put in there. And the groups that you put in there, and that raises all sorts of things in bifurcation theory and all sorts of things, right? Is GL3 plus, the way I said before, but it could be this group K3, which is some kind of a conformal orthogonal group, see there is a coefficient here, lambda, or the orthogonal group itself. And then they have names, micromorphic, microstretch, micropolar. But we can imagine other groups. I mean, that's the beauty of it. I mean, we can imagine all sorts of other groups here. This has not been done. So the general theory admits other groups. Now we are going to study in this discussion only micropolar fluids. So my order parameter group will always be denoted by O, because it's an order parameter group, and it's going to be in this discussion SO3, nothing else. I'm simplifying a lot what we have done. So here comes Erringen. Now, I tell you as a mathematician, I mean, you may laugh, but for somebody who knows nothing, and is a mathematician, all I want is, please give me the equations, right? That's all I'm asking. And this is not an easy thing to ask. And in fact, that's the problem. You look at Erringen, and you go for 50, 60 pages, right? And here is what you find. I'm saying that these are Erringen's equations, but that's not quite correct. I'm coming to this. We had to add to them. So you look there and you say, this is a good one, the first one. This, any fool can see what this is, right? There is some Euler equation here. You see the gradient of some pressure, and there is, of course, something else. Great, I understand this. Then he writes this down. Well, there is no ddt there. This is bad. But he keeps repeating it's important, so you put it, right? Then you say, well, I better have mass conservation, and sure enough, he does it, right? You find the mass conservation equation there. So that makes you happy. You understood two equations. There is something else here that, okay. Then there is another equation here that you probably don't recognize, but people doing geometric analysis know what this is. These are equations for inertia tensors of the rigid body written in spatial coordinates, not in body coordinates. I mean, my students, for example, would know this because I give them such an exercise. Right? So it's, this is good. This is the blob that's moving, and because it's moving, it has some equation. I start understanding something, right? And then you keep looking for equations, and you find no more. And now you're in trouble. No, but if you look carefully, you realize later that the sigma k, in fact, has DDTs. Good news. So this equation, in fact, has a DDT. It is a dynamic equation. Okay, you can plug it in there, and then you get something. Okay? You still have a problem. You don't have enough equations. And then you keep reading and reading and reading, and there is no equation coming. Okay? But Erringen keeps telling you that he has this new variable. Let me start naming them. For those of you who are geometers, this is horrible. All index gymnastics that you have learned is being ignored by Erringen, right? Up-down indices, which is very important. Everything that's repeated is summed, regardless of position, okay? Then u is the Eulerian velocity. This is the mass density in the space. Mu is the micro-rotation rate. That's so correct because skew 3x3 matrices are, in fact, Lie algebra isomorphic to R3. So that comes from the group SO3. This is good, right? This is moment of inertia. Obviously, it's a function from the domain into symmetric 3x3 matrices, okay? And this sigma k is called spin inertia, okay? Now there is this mysterious Reines tensor, which in Erringen appears both with 3 indices and with 2 indices, just to make sure that you get confused, right? But the distinction is important, because when he has 3 indices, and I put different indices, he doesn't, for him it's all ijk, right? These are Lie algebra indices, and these are space indices. And then he identifies SO3 with R3, and now suddenly you have 2 indices because not a matrix anymore, right? Okay, fine, no problem. And what does he do? He says, well, he more or less tells you this. He doesn't write it this way. Eta is the diffeomorphism, then you take the gradient of this and you multiply by chi minus 1, and then you realize it as a vector. This is the hat map. The relationship between the matrix and R3 with a cross product as the Lie bracket.
Is that related to the spinning angular momentum?
Yes, absolutely. Absolutely. This is a very important variable. So he keeps telling you that I can do this. Of course, he doesn't. I wish he would have told me that, but okay. Eventually, I understood this is what he's saying, right? So now we have to add one more equation. So this is this equation in Ehringen notation. So this equation is what Ehringen should have written had he taken the time derivative of what he says with an initial condition which is different from 0. Right? Let me repeat this. He has some initial condition for gamma that is 0. Right? That makes his life easy. And there is a price he pays for this, a big one. But if you wouldn't have taken it 0, and if you take what he says that he should have said, and take the time derivative of this, this is what you get. Now we have all the equations. Okay? So these are the Ehringen equation. Okay. So now, of course, the question is the same, right? I'm playing the same game. What is the variation or Hamiltonian structure of these equations? What is the relationship between these two descriptions? Now, Ehringen, as I told you, claims that under certain hypotheses, and the hypotheses are a rod-like assumption, or it better be like this, because that's what Erikson Leslie says, with the choice gamma equal to grad n cross m. Now, you will see that this is absolutely impossible. This is false. I mean, once I explain to you the geometry, it's completely obvious this is false. It cannot be right. Okay? There are other subsystems, however, in the Ehringen system, and this is, I want to sort of provoke. Yeah?
N has indices, and so does grad, which is cross.
Yes, this has 2 indices, this has 1 index, you take the cross product, you get a vector, correct? Yeah.
What?
I will tell you what gamma is. Just wait a second. I will tell you what gamma really is. At this point, it's just like this, right?
Okay.
There are other subsystems here which are called G strands, and this is ongoing work with Francois and Daryl, and that has to do with when J is equal to constant. Okay. Now, the statement has created controversy. This statement that Ehringen said explicitly, I can do this. Okay? Here is a paper in 1919 by Rimars who says, no, it's not possible. You have to add things to the potential energy. Maybe then it works, or I can get it to work partially or something like this. Ehringen, of course, says, no, that's not true. Look, I have another paper, and I'm going to prove all of this for you. Right? And he says explicitly, in italic, the O-Fell theory, this is Erikson-Leslie theory, is a special case of E theory. E is Ehringen himself. Right? So, and that's where the situation lies up to now. So we are going to solve this problem. We will show under which assumption Ehringen reduces to Erikson-Leslie, and we will establish the correct relation between gamma under these assumptions. The bottom line is that both Ehringen and this guy and his detractors were partially right. Or partially wrong, depending on how you want to look at it. Okay, so here is the workhorse. I'm not going to go into too much of geometry, so I chose the Lagrangian path. You could choose the Hamiltonian path. We have the description either way you want. You can give you brackets, we can give you whatever, right? But this is quicker, it's easier, it's more in the spirit of this. We are talking about variational principles. So I want to show you the workhorse on the Lagrangian side, and this is a theorem of Poincaré in 1901. It's a 1.5 page paper in which Poincaré doesn't say why he did it, doesn't quote anybody, never did anything like this before, never did anything like that after it. It's a brilliant paper. And the paper is literally what I'm telling you, except he uses the group SO3. But this is ridiculous. I mean, all you have to do today is calligraphy. You change the SO3 with a German G. Right? There is neither here nor there. He really knew everything. So, the problem that he poses is the following. Let's assume I have a Lagrangian whose configuration space is a Lie group. Okay? So the tangent, so this is the state space, TG, the Q's and the Q dots. And this is left or right invariant. I'm going to show you here on the left, then I'm going to show it to you on the right because I'm going to do fluids. And then he says, well, let me take a curve let me take the derivative of that curve, that's a tangent vector at a certain point, bring it back to the identity, I get something in the Lie algebra. Now I have a curve in the Lie algebra. And he says 4 things are equivalent. G satisfies the Euler-Lagrange equations for L on G. The variational principle of Hamilton holds for variations with fixed endpoints. What we call today the Euler-Poincaré equations hold. I will tell you what this notation is in a second. And the Euler-Poincaré variational principle holds for variations that are constrained. It's not really a variational principle in the classical sense. It's some kind of a constrained variational principle. But the constraint is in the variations themselves. Okay, so let's see what is obvious and let's see what's not obvious here. And what are the notations? First of all, add xi means is the linear map that says take the bracket with xi. It sends an other element in the Lie algebra eta into the bracket of xi with eta. Star means take the dual map between the dual spaces with the arrow reversed. Okay, the plus and the minus go with left or with right. This is left, this is right. They correspond. Okay, what else do I have here? Okay, no, everything is, the notation is clear. Del L, del xi are functional derivatives. The way you know and love them and you compute them. No problem. So what is obvious? Obviously, 1 is equivalent to 2. I mean, it has nothing to do with Poincaré. This is Hamilton's variational principle. For any Q, anywhere you want. We all know it from our elementary classes. So nothing is new here. We can even prove that 3 is equivalent to 4 in our head. That's how easy it is. I mean, let's do it. If I take delta here, what am I going to get? I'm going to get delta L delta xi times delta xi. I plug delta xi here inside, and I integrate by parts and to get it on the other side. What am I going to get? An expression times eta. Well, this expression is going to be this minus that times eta for any eta that vanishes at the endpoints. Well, fundamental theorem of calculus of variation, that factor is 0. So here are the equations. This is the equivalence. Now let's prove that 2 is equivalent to 4. Well, you say, well, watch, I mean, L is invariant under G. So if I multiply by G minus 1 here and by G minus 1 here, nothing changes, right? That was my hypothesis. But G minus 1 G dot is called xi. So obviously the integrands, let alone the integrals, are equal, right? So where is the content of the theorem, right? The content of the theorem is here. This is non-trivial. It's not difficult, but it's not trivial. So let me explain what's going on. I tell you where this comes from. So when we want to do the variational principle of Hamilton, what do? Well, we take 2 points, right? We take a curve, and then all the variations of all the possible curves. So we have a parameter that moves the curve. Let's call it epsilon, right? By the fundamental principle that if you have nothing better to do, you take a derivative, you're going to take a derivative relative to epsilon, right? When you take a derivative relative to epsilon, you're on the group somewhere there. Bring it back to the identity. You get somebody in the Lie algebra. Now, you're going to get somebody in the Lie algebra depending on t and on epsilon, right? Question, do you get everything? If I take dd epsilon at epsilon equal to 0. No, that's the surprise. What you get is precisely these delta x's, no more and no less. So these delta x's are such that there exists an eta, arbitrary, such that delta xi is eta dot plus or minus xi eta, where eta t is an arbitrary path in G that vanishes at the endpoints. Eta A is equal to eta B, and is equal to 0. That's the lemma that needs to be proved. But okay, you prove it, and Poincaré did it, and it's true, and that's it. Unfortunately, okay, let me tell you more. This is good news in some sense, because the geometry has led to analytic questions. We have a variational principle, right? So we should be able to do something analytically at this point. I'm not aware of any sort of heavy theorem dealing with such types of variational principles. And John, please correct me if I'm wrong. I have not seen anything. I wish I could have seen something, because I would love to start quoting theorems, right? The other thing, what this does is you have the reconstruction method. The reconstruction basically says something very simple, that if you have solved the problem for little l, you've solved the problem for capital L. But notice that, that this is quite an achievement, because here you have half the variables than you have here. That's the miracle of reduction. I mean, for us in geometric mechanics, we know this. you get half the variables for free if you know what you're doing. Okay, so this is what's happening. So let me solve for you the problem. Imagine that you can solve the problem with only the Euler-Poincaré equation. So 4 points. Well, you restrict. Thank you very much. That's easy. The second one, you solve the problem. You solve this equation. This equation is a lax equation, right? If G star is equal to G, for example, the Lie algebra is semi-simple. So you need to solve a lax equation. So for example, this may be an integrable system. And if it's not, don't panic. There are variational integrators. Solve it numerically. There's a whole industry of people doing this, right? Many of them in geometric integration. They use this variational principle to numerically integrate. Okay, so you solve this. So if I solve this, the rest is finished. Solve the linear equation with time-dependent coefficients. So if I play the physicist, time-ordered exponential, and I'm done, right? Whatever that means. We call it quadratures. And now you have the formula. If I give you an initial condition, write it as G0 times Xi0, right? Then the solution of the problem is V of t is equal to G0, G of t, Xi of t, where Xi of t is solved from here, and G of t is the solution of this. Finished. I solved the original problem. Okay, so this is called Euler-Poincaré reduction. This works, for example, for free rigid bodies, ideal fluids, KdV, and there are important extensions that were done 14 years after we did the Lagrangian, the Hamiltonian part, because, okay, I'm not going to go into that why. There were problems, and this is in this paper, found in this paper. And then there was this impetus of this paper of Holm on the geometry of complex fluids, who got us sort of on the right path. Okay, I need to go more abstract. I'm sorry, I have to tell you a big theorem now. So I'm going to extend the Euler-Poincaré theorem to things with parameters and things that sort of tag around. This is the gamma that you have seen in Ehringen. Okay? So I'm going to have a group that acts on a vector space, and then it introduces, you have a representation, introduces all other representations on the dual, the Lie algebra, and the Lie algebra on the dual. These are called, they're all named contragradient representations. My terminology is always that if I act on the right, I act on the right. So VXi means Xi acting on the right on V. GV means G acting on the right on V. And in addition to that, we have standard duality pairings between the space and the dual. And then we have something which is an affine representation. And the affine representation is going to be on the dual of the vector space. These are the advected quantities. That's why you have to think of them like mass, entropy, magnetic field in MHD. There is this coefficient C. Now, I wrote what this is supposed to do, but you don't need to remember this. All you need to know is that whatever identity C needs to satisfy, so that this is an action on the right, is in fact the famous identity that algebraists, our colleagues who are just doing the other workshop, know very well, right? They're called cocycles. They're called group 1 cocycles. They have to do with group cohomology and also some other things, so there's a lot of topology already hidden here. Okay. Then what I need to do is I have to take the infinitesimal generator of the action, so I write it here, and this dC is going to be simply the derivative, the identity of C applied to Xi, and to make it my notation simpler, I just call it dC. It's a derivative. Okay. Now, we need to introduce various things. First of all, I need to introduce the transpose.
Go back a second.
Yeah.
I'm George. A lives where?
In V star, in the dual space.
So that theta really is the convective derivative.
There is no derivative yet.
But it will be.
Yes, when I take derivatives.
G will be.
When I put G of t and when I take ddt, things will happen.
What's A then?
A is going to be an advected quantity. But it's more general because the gamma is not advected in the usual sense.
There's no gamma on this.
Not yet. Just wait. It will come. That's the point. Okay. I need some operations. I need to take some duals. I call them transpose. Here it is. I just take the transpose relative to the duality pairings. And I need a certain operation here, which I call diamond, which is defined in this fashion. So it simply tells you that if I have an element in the vector space and an element in the dual, I will get something in the dual of the Lie algebra. So I have to feed it an element in the Lie algebra, and it must spit a real number, right? And that's the real number it does, right? Okay. And then all sorts of things happen. For example, what is the dual? You use the duality pairing and you get this. And now I form the semi-direct product of G with V. So that's a new group. And this group has a multiplication rule. And this multiplication rule is given in the following way. G1, V1, G2, V2 is you first multiply G1, G2. And here you is V2 plus V1, G2. Euclidean group. Think Euclidean group. SO3, semi-direct R3. In a concrete example. And of course it has a Lie algebra, and the Lie algebra has to be given to you, and there are methods how to do this, and you compute it, and here it is. This means that psi2 acts on V1 minus psi1 acts on V2, and then you take the dual of this map, and I tell you what the dual of this map is. For those of you who know some symplectic geometry, this is the momentum map, but I'm not going to go into this. Okay? So there are other links with the completely different field which are extremely interesting. This is literally the momentum map. Okay, so in a physical problem, what are we given? I mean, this is all nothing, this is nonsense, right? I'm given a Lagrangian that depends on parameters. Compressible flow, right? The material density is a parameter, right? The initial magnetic field in MHD is a parameter. So I'm not in the situation that I was before. Right? I could ignore these parameters if I want to, but it's at my own peril, as you will see in a second. So, in addition to that, this Lagrangian is invariant under a certain group action. And I give you the group action here. It's complicated. It comes from the semi-direct product. This is true in all these physical systems. Heavy top, compressible flow, MHD, I can go on. Quasi-geostrophic flow, whatever. So if I freeze the parameters, then I have a Lagrangian in the usual sense on TG, just by freezing it, right? And this is invariant, and this is the catch now. I have broken the symmetry. It's not going to be invariant under the full group, but only under the group that leaves invariant A0 relative to the affine action. That's why I put the C up there to remind you that this is a co-cycle. So for example, if A0 was 0, this is not the whole group G. Even then it's not the whole group G. And there is the right invariance of L, and that permits us to introduce a new Lagrangian, which now depends on other variables that you haven't seen before. It depends on a Lie algebra variable and on an element in the dual of the representation space. Okay, so I'm going to play the same game as Poincaré. Let psi of t be g dot g minus 1. I'm going to do fluid. I'm going to be on the right all the time. And a of t to be theta gt minus 1 a0. You see, I put it on the right. It's gt minus 1. Then a of t is the unique solution of the following affine differential equation with time-dependent coefficients. Here it is. This is one equation that I already have. And I know its solution. No, quote unquote, right? Because I don't know g of t, right? Good. The following are equivalent. And here is exactly the 4 points like in Poincaré's theorem. When A0 is held fixed, this Lagrangian, this classical variational principle, is equivalent to the Euler-Lagrange equation. There is a constrained variational principle, and there are affine Euler-Poincaré equations. So the constrained variational principle says that the variation of L of psi of t and A of t is equal to 0. Upon variations, this we have seen before, exactly the same ones, but there is a second constraint, what variations you can take on the parameters. Here they are. And the affine Euler-Poincaré equations hold, and you see the first term is exactly the term that we had before. So if I would erase these two terms, it would be exactly as before. But now it's not. There is another thing that involves the parameters, and the term that is sticking out there relative to this C. Okay? Okay, so this is an abstract theorem. What do you do when you have complex fluids? I want to apply this theorem to complex fluids, and I will apply it twice. So there are two things. Complex fluids have internal degrees of freedom, and there is a new kind of advection. This is the equation that Ericsson would have written had he blah, 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 right? As I told you before. What does this mean geometrically? It means that I have to enlarge the particle relabeling group, which used to be the diffeomorphism group of the domain, to the semi-direct product of the diffeomorphism group with functions from the domain into the order parameter group. And the second thing that I have to worry about, the usual advection equation for mass, entropy, magnetic field, need to be augmented by a new advected quantity in a new sense, in another sense, on which the group G acts by an affine representation. These are the two things. Okay, so what do you do? So I have to explain to you now, what am I doing? So here is the group, here is a vector, here is another group. I have to act with this group on this group by group homomorphisms. And it's true, this is the action, just change variables, right? I relabel the particles on the right, and then I have, according to the general theory, I have a formula for group multiplication. So this is composition, this is composition, this is multiplication in the group, that's why there is no sign, just concatenation. Okay, I fix a volume for mu on D, okay, so I identify densities with functions to simplify my life. I have a Lie algebra, and I have, in the Lie algebra, I have, I know what the bracket is, and here is the bracket. All I want to tell you is that this bracket, all these operations here are taken pointwise. Let me stop there, I don't want to go into more details. I form the dual of the Lie algebra. The dual of the Lie algebra is going to be forms times functions with, from the domain D with values in O star. Let's call them M and K. What is the pairing? The pairing is the usual L2 pairing. What else can I do, right? And then I have to compute, as you have seen, in order to write the equations down, I have to compute this coadjoint action. Again, I don't want to go into this. They are all taken pointwise. All these operations make sense. The formulas here are not very important at this level of the talk. It's only important that you know that they exist, you can pick them up, and you can compute with them, right? It's not there exists some. No, it's there. So what do we do with Erickson-Leslie? In Erickson-Leslie, the symmetry group is exactly the group that I told you before. I'm going to call them exactly as before, eta chi. The advected variables are functions and vector-valued functions. I call them rho and n, mass density and director. The representation of G on V star, after all, this is all we cared about, is J of eta. This is the Jacobian of the diffeomorphism. This is because it has to do with densities. And this, here is the representation, how rho u is transformed. And there is an associated infinitesimal action and the diamond operations in order to be able to write down the equations explicitly, right? Here they are, I can compute them, and there is no cocycle, right? Simple as that. I apply the theorem, right? I mean, I'm going by the book. I have a theorem, apply, right? Sit down and compute. It's no more difficult than this. So you sit down and compute, right? Here is what you get, these equations. Okay? They're not Erickson-Leslie, okay? The reduced Lagrangian depends on all these variables, and you can see it's a beautiful Lagrangian. Look here, the kinetic energy, 1/2 mv squared for the fluid, 1/2 j omega squared for rotations, right? It's little rigid bodies that rotate. Here they are, minus some internal energy. Okay. So, I compute for this specific Lagrangian, the Euler-Poincaré equations, and now they start looking much better, right? Look at this. For example, here's mass conservation, right? Here is the usual piece of the Euler equation here, etc., right? How do you get Erickson-Leslie out of this? So here is a little lemma. If nu and n are solution of these Euler-Poincaré equations, then if the initial condition is 1, it will stay 1 for all time. If the covariant, if the material derivative of the dot product is 0, then it will stay so. In other words, initial condition is 0, it will stay so for all time. Suppose that these are true, then d dt of n is nu times n, becomes nu equal to this, and rho j d dt of nu is h times n, becomes one of the Erickson-Leslie equations. Therefore, what have I proved? If u nu rho n is a solution of Euler-Poincare with initial condition n0 and u0, satisfying these two conditions, then this is a solution of Erickson-Leslie. And conversely, if u rho n is a solution of Erickson-Leslie, I define nu to be this, and I get the solutions to the other one before. So I replaced Erickson-Leslie by these equations. They're all first order. Okay, good. Erringen. The symmetry group, of course, is the same. Now there are advected variables. The advected variables are going to be functions, real valued functions, functions with values in symmetric 3 by 3 tensors, the moment of inertia, and one forms with values in the Lie algebra SO3. Those of you who are geometers should jump off joy at this point, right? What are such objects? Connections. Right? If it walks like a duck, it is a duck, right? The representation is, it's extremely interesting. The representation is going to be as before, except it acts linearly only on the first two terms. And it acts in an affine manner on the third term. I mean, if this is not a connection, I don't know what is. This is the law of transformation of a connection. It's like Young-Mills. So gamma transfers a connection. Gamma is a connection. Okay? Now, I'm done, right? Take the theorem, compute. Right? You take the theorem and compute. This is what you get. The Lagrangian is going to be defined on this space. Here is its expression. Exactly as before. 1/2 mv squared for macro motion, 1/2 j omega squared for rotation, minus internal energy. Now, it depends on these other variables, of course, right? And the affine Euler-Poincare equations are, here they are. Now, first of all, these are the Erringen equation. If you are now sitting down and plug in idiotically all the indices, right, you will get exactly the Erringen equations that I wrote down. Please look at this equation, as the last equation. See, this is advection. This is advection. Right? It's completely obvious. If this term wouldn't be here, it would be in usual advection. This is the Lie derivative. Lie derivative means you drag it along by the flow. Right? It's not dragged along by the flow. There is another term here, but it's dragged along by something else. Right? Because this is a connection. So this is a very interesting equation. This is geometric. This is the covariant derivative relative to the connection gamma of nu. In our case, it's completely clear who it is. I mean, I can write it down. D gamma nu of v is the derivative with the bracket. Just like this, literally. That's what it is. There is no mystery, right? So this is the new type of advected quantity that you get. This is what Erringen has. Okay, so this general affine Poincare theory can apply to many systems. We have a 100-page paper where 70 pages are only examples. Is this one? Do you get something out of it? Yes. For example, do you want to see Kelvin-Noether theorem? Sure, no problem. Here is one for u. Here is one for gamma. Right? For example. So this is giving you something. In addition to that, immediately. Okay. Now, Erringen implies Erickson-Leslie. How does this go? So physically, the Erringen equations should imply Erickson-Leslie. It's completely clear, right? I mean, these are blobs. If I suddenly make the blob like this, and I make it into an arrow, just intuitively, I mean, it better be like this, right? So Erringen proposes, I remind you, take J to be this, and take gamma to be this. Okay, this is false. I mean, just plain mathematically false. Why? First of all, there are two arguments. There is a brute force computation. Just sit down and check. It's not going to work. Right? You can do this. I don't advise it. I've done it. It took us with François about 2 days to do this. The computations are horrendous. Just to have peace of mind. It doesn't work. It's not. You don't get equations. You get something else, very close, but you don't get it. But you can see by symmetry consideration that it's not true. It cannot be true because if you say that this is true initially, it will not stay true afterwards. Why? Because gamma transforms like a connection. You have other terms that come there. So this cannot possibly be true. Okay. However, not all is false. Erringen came close. It is true that there is a psi of j and omega such that, this is little j, remember, right? Such that this is like that. This is already a good indication. And the definition of this, of j, is geometrically consistent. If initially it's like this, it stays like this. So he wasn't too far away. Incidentally, this is the only mistake that I really found in Erringen, in a volume like this. Now imagine that this guy computed with this algebraic structure that I just gave you, with the semi-direct products. I mean, I'm amazed how he did it without mistakes, without knowing it. Okay, so here is how this goes. Roughly speaking, here is what we do. You cannot compare, at least we couldn't, directly Erringen with Ericsson-Leslie. We are going to build two new equations. One equivalent to Erringen, one equivalent to Ericsson-Leslie. There we compare, and there we will see. Okay. So the first thing we have to do is we need a gamma formulation of Ericsson-Leslie. Ericsson-Leslie doesn't have the gamma, right? So how do we do this? So you look at the material Lagrange and you go back to basics. Everything has to come from the material representation by reduction. This is, I mean, for us doing geometric mechanics, this is religion, right? You go back to basics, you go to the material representation, look at symmetry, reduce. You will get something, always, guaranteed. So I look at the material Lagrangian, here it is, chi and chi dot. Forget the fluid motion. The fluid motion doesn't matter. It tucks along and it's easy. These are liquid crystals that don't flow. We can add the flow afterwards. This is not, the problem is here. Okay, so I write only the part that has to do with the liquid crystal. And here is everybody in. Well, I mean, if I don't want chirality, I can kill Ki2, right? And I am going to apply, the fundamental idea is I'm going to apply two reductions. So the first one goes like this. Well, this guy here depends on this parameter. So this L and 0 is from the tangent bundle of some configuration space, which is this one, this function space, and it's invariant under this action. And therefore, you're going to get a Lagrangian in new variables. Here it is, right? You write the Euler-Poincaré equations down for it. Again, the same thing over and over again, right? And here they are, the dynamic equations. And here are the equations written explicitly if you plug in everything. And by the time you're finished, whoops, this is Ericsson-Leslie. It's exactly the equation that doesn't involve the macro motion for Ericsson-Leslie. It's the micro motion. And that's what I'm after. Good. Here it is. Good. No problem. I start now with the same Lagrangian. And I look at it in a different way. I think that there would have been a gamma there, which happens to be 0. Okay? Why not? Now, this new Lagrangian is invariant under the action, but of course, there is another variable here right now, right? Well, I carry it with me. And I compute the isotropy group, because I have to look what is the symmetry group, to what I have broken the symmetry, right? This turns out to be just a circle, in fact. This is this mysterious GA0C in the general theory for this particular example, in this situation, right? So we are going to get, by general theory, a new Lagrangian, call it L2, there it is, where this new, sort of as a, if you think of it as a skew-symmetric matrix, is chi dot chi minus 1, and n is chi times mu 0. And gamma is this, okay? So it's a one form with values in matrices. It's a connection. So, therefore, now you see immediately what is the relationship that Erringen should have written. The correct relation between gamma and n is grad n is n gamma. This does not define gamma. Ehringer has tried desperately to define gamma and get it in the equation. You cannot do it. There is a relationship between n and gamma only. Okay? As you will see, no problem. This will get us going. So the notation is the usual one. This is completely the obvious one. But how do you apply? What does it mean, the cross product that you asked me a moment ago? You know. Okay. There is an important remark here, which is subtle, which I'm going to gloss over. This object here, this Lagrangian, depending on these parameters, may not be defined when gamma 0 is different from 0. In fact, I may not know it. This happens in other physical problems that we have dealt with, like strands. And therefore, geometrically, this means that L2 is defined only on the orbit of gamma 0, coadjoint orbit. This does not affect reduction as long as this expression is invariant under the isotopic group of gamma 0 equal to 0. So there is a theorem that lets you know you're okay if you check that much. Okay? So if you ask me what is it for gamma 0, I do not know, but I don't care. Okay, I compute the Euler-Poincaré equations. Again, the same recipe over and over again. I compute it. Here they are. Okay? This, if gamma 0 is different from 0, these reduced equations still make sense, and they are an extension of Erickson-Leslie dynamics. And they account for disclination dynamics. I gained already something, even here. Okay? These equations have consistently preserved this relation. Here is the proof. And here is a little theorem. The Euler-Poincaré equation for L1 and the affine Euler-Poincaré equation of L2 are equivalent. And the argument is they come from the same Lagrangian by reduction. Same material Lagrangian by reduction. In addition, the affine Euler-Poincaré equation allows for a generalization of Erickson-Leslie to the case with disclinations. Okay, step 2. What do I do with Ehringen? Let me recall for you what happens in Ehringen briefly if I don't have the fluid flow. Here is the Lagrangian. It's written explicitly down in all its glory. The variables are J0 and gamma 0. I0 is this combination. This Lagrangian is invariant under a certain action, the same one that I showed you before. I'm not inventing anything new. The reduced Lagrangian used to be this. In fact, it has still an 1/2 mv squared, like rho of u squared, but this is now gone. And the Ehringen equation are the affine Euler-Poincaré equations for the group G, and V star is equal to this. Right? This is what we discussed before. So now I put the rod-like assumption. So that the first sub-step here is I put the rod-like assumption. So I say that J0 is equal to this. This definition is invariant under this group action. So that means that this is true for all time. Now I take my material Lagrangian, I write it down explicitly with all its parameters, and this is invariant under the action of the correct group. This being this the symmetry group, the group to where the symmetry has been broken too, right? I have a new reduced Lagrangian L2 prime. Here it is. Lemma, affine Euler-Poincaré equation for L2 prime are equivalent to Ehringen's equations in which the rod-like assumption has been assumed. Okay, it remains to show that this equation contains, as particular case, Erickson-Leslie. I'm finished, right? I have Erickson, I've done this. I have Ehringen, I've done this. Now I have two other models. I'm comparing now. No disclination assumption. So we do exactly like Ehringen has said. We don't have disclinations. You put gamma 0 equal to 0. You do exactly as before, and you suppose that S0 is constant and take gamma 0 equal to 0. The evolution is given in this fashion. And since n is equal to chi times n0, a computation shows you that you get the relation that I advertised before. Okay. Now comes the crunch. I have to recover the Ose-Frank-Zöcher free energy. Yeah? So that's a computation, right? So here it is. Again, if I want pneumatics, I kill this term, right? So I need to show that there exists a function of j and gamma such that psi of j and gamma is f of n and grad n. Yes. After pages of computations. There is nothing, there's no genius work here. This is muscle, right? You just sit down and compute, right? True, there it is. So we can rewrite the reduced Errington-Lagrangian in the rod-like assumption in this fashion. Okay, we have L prime, and now I can replace the internal energy by this. Why not? This is exactly what I just did. So the same substitution yields the unreduced Errington-Lagrangian in the rod-like assumption. And now I recover it. How do I do it? I interpret now this material Lagrangian as a Lagrangian depending on a parameter, exactly as before. I check that this Lagrangian is invariant under the correct group. I implement Euler-Poincaré reduction associated to the action and obtain the reduced Lagrangian, right? And by general reduction theory, there are theorems that back me up, the Euler-Poincaré equation for L1 prime and the affine Euler-Poincaré equations for L2 prime are equivalent, since they are induced exactly as before by the same Lagrangian, different symmetry from the material representation. Okay, it remains to be shown that the Euler-Poincaré equations for L1 prime are Erickson-Leslie. Yes, they are. Sit down and check. It's easy. So the theorem is the Erringen micropolar theory of liquid crystals contains as a particular case the Erickson-Leslie director theory. More precisely, to be precise what I'm doing, the Erickson-Leslie theory is recovered by assuming rod-like molecules, here is the formula, and the absence of disclinations. That's how you get it. It's exactly what you want. The summary, this is shown using Euler-Poincaré reduction and allows us to replace Erringen's false definition of gamma with a certain relation. And that's it. This is not so important.
Okay, thank you for
I
your
believe
talk.
that,
Please,
that
yeah.
Holger Stark and I, some years ago, derived essentially what you have in a totally different language.
We didn't know.
Well, I didn't know about this either, so it's,
This is new, so I should have known.
the point is that the Leslie Erickson sort of misidentifies what the angular momentum of the spinning rods are. And so you need to put that in as a separate variable from M. And as far as I can tell, looking at your equations, we have essentially the same thing.
Oh, I think you, I see. So these equations that I did, in which I added the new,
Yeah.
is what you say that.
Yeah, it's that you really need an angular momentum telling how the particle spins, whereas Leslie Erickson said that the angular momentum energy was m cross n dot squared. And that is a guess. There's no, that the rods are spinning. And so if you put that in, then you get a complicated set of equations, and then the correct limits, which look similar to what you have, you regain Leslie Erickson. But we have dissipation, and there's the
Yeah, I have no dissipation here.
So I'll give you the reference.
Yeah. Thanks.
It seems to me that inertia plays a crucial role in your,
Yes.
and also, I mean, this is also manifested in the expression you recovered for the Frank's elastic constant, because they go up to infinity as j goes to 0. I mean, can you comment on this?
I mean, I never took any limits here. I mean, for me, I don't know how to say it. It's these are initial conditions that I can put. It's not that there is some parameter whose limit I take, right? I literally take these initial conditions, right? The J0 is of this form, the gamma 0 is 0, and then I show that Erickson-Leslie is literally embedded in it.
Oh, well, my only point is that it looks a little bit odd to imagine that the elastic constants are proportional to the reciprocal of the inertia. That's my...
I see. Talk about this. I want to understand what you're saying more precisely.
What I mean, the dissipation is missing for this is...
Yeah. So this is, incidentally, probably the second mistake he's made, but I'm not sure it's a mistake. He defines symmetric by taking trace relative to... This cannot possibly be right. I mean, any geometer will jump out of bed when he will see this. Right? You cannot take traces of a Lie algebra indices of the space indices. It's just not possible. Right? It just happens to be 3 here, right? But maybe some projection is needed. In any case, what he says is wrong. But maybe he's trying to say something else, which I didn't understand. But I know how to find symmetric, but I don't know enough invariant theory to be able to tell you what kind of invariant function I need to take in order to define. Give me invariant functions and I define for you all sorts of liquid crystals. I mean, it's clear how to do it.
Please.
So in your lecture, Tudor, the gamma zero comes and goes. And here on this last slide, there's gamma zero again. Is gamma zero related to, or discontinuities or
Yes,
dissociations?
yes. So Ehringen himself never put gamma zero different from 0. He never talks about a gamma zero even being possibly different from 0.
So he has no defects in his initial
Right.
in his initial conditions, and without dissipation, no defects will form.
Right.
But if you have defects in your initial conditions,
Then they will develop. But according to this new type of equation that quote unquote advects a connection.
is this curl of this gamma zero, that's the density of defects? Or is that stretching too far?
That I don't know. I wouldn't stick my neck out to say that. I have to check. I don't know. I truly don't know.
Interesting, because the description you give is that this is essentially a gauge theory, but
Yes.
more related to general relativity
Yes.
than Mills. So the two questions are, one, you say that there is no analysis on this, but maybe don't you think that you can import the analysis on that?
I agree.
And the other question is that if it is a gauge theory, then gauge theory can deal with the non-trivial topology. So probably you can have, if you change the topology, you don't have Erickson-Leslie, but you have something else.
Absolutely.
You have a prediction of theories.
Yes, absolutely. And you can take various things. I mean, I learned, for example, just being at this conference, things that I never knew before. I mean, what is Orsager? I have no idea, right? But better be here, right? Somehow, I don't know where, right?
Okay, so maybe I suggest that we stop at this point. Of course, I mean, discussion can be continued overnight. So let us.